Hello students, let's learn about rational functions today. Rational functions are the functions of the form p of x over q of x. And since this is in a fraction form, we must take care that q of x cannot be equal to 0. But what are these p of x and q of x? They are polynomial functions. They are polynomial functions. And we must make sure the denominator cannot be equal to 0. So why? If it is 0, definitely the function will go undefined, isn't it? So the simplest form of rational function is a reciprocal function, and it is given as 1 over x, correct? So this is a simple introduction, but there is much more to it. The premise that the denominator cannot be equal to 0 is actually giving rise to some important concepts in rational functions. So an asymptote, what is an asymptote? So we'll come to the details of that. So details of the rational functions. But first, what is an asymptote? Asymptote is a line, pretty much actually. It is a line on which the graph seems to approach, but it never touches. It never touches. It seems like it is, but it never does. So in this graph here, if you actually look at it, I'll use different colors. So if you see here, this is blue, and let's try green. And this is the green one, the vertical one. So there is a vertical asymptote and there's the horizontal asymptote. Why is that they have two? So we know definitely that x cannot equal to 0, right, in this parent function, or this is a different function, but and we need to figure out what that is. But what is the equation of this particular line? It is like 3 units to the left of the y-axis, so this is definitely x is equal to -3. And this particular guy here, which is horizontal, it starts with y because the y value is 1 and it's 1. Yeah, so y value is 1. So these are the places where there are asymptotes, meaning the y and x values are not defined in this particular rational function for this particular places. So the vertical asymptote is, in this case, x equal to -3, because the vertical asymptote starts with x, right? That's they are the points on the x-axis. And horizontal asymptote starts with y equals 1 in this case, right? So in addition to these things, why is this coming? If you actually assume that the stretch factor is 1, then the rational function here would be 1 over x plus 3 plus 1. This is how the rational function looks like for this particular graph, because it's of the form a over x minus h plus k. So this is not the only way a rational function is represented though. So it could be represented as p of x over q of x, just like how we have defined it here. In effect, even this becomes p of x over q of x. It's if you actually add these two fractions, that's the kind of function you would get. So what if there is a quadratic on the top and some other polynomial at the bottom? Then how does it behave? So there are different things to it. The first thing you would actually see is that there will be a hole in the graph. So what is this hole? If you actually put this even into Desmos, it will show as this particular point as 2 and undefined. Why? Because it's part of this rational function, but it could be removed, because if you actually write a function in factored form, and if you see that a numerator and denominator have the same linear factor, which could be cancelled or removed, then that becomes the hole, or the removable discontinuity as it is called, or there is a break in the graph. So which means that at that point x equal to 2, there is a hole or a break in the graph. Okay, so when we are given a rational function, the first thing you would do is write it in a factored form. So a factored form, right? And then I would actually first find the vertical and horizontal asymptotes and then find x and y intercepts, right? And then hence we can write what are the domain and ranges of the function, and also draw the graph, right? So now let's look one at a time. And there is one other thing that I have to mention, and I'll do that as I do an example also. So here, for example, here there is one factor that is left out in the denominator. Even this is a potential case where the function could go undefined. When x is equal to 1, that is when it goes undefined, and hence you have an asymptote, a vertical asymptote at x equal to 1. Excuse me, x equal to 1, right? So this is the whole, but here x equal to 1 becomes the vertical asymptote, VA for short, in short. And then how do I find this horizontal asymptote if I don't have the graph? So normally what we would do is actually expand this. In an expanded form, the same function f of x would look like x minus 2 over x squared minus 3x plus 2, isn't it? Then the exponent, or the degree of the numerator and the degree of the denominator are considered. In this case, the degree of the denominator is greater than that of the numerator. So there are some acronyms for us to easily remember these three cases where the degree of the numerator may be the same as the degree of the denominator, or degree of the numerator may be greater than that of the denominator. So these three cases are here defined below. So this is when all these cases are considered when you are planning to find the horizontal asymptote. I'm talking about the horizontal asymptote, okay? So the degree of P over Q, right? P of x over Q of x, that's the reference. So meaning the degree of the numerator is greater than that of the denominator. So how would I write it? So we will write it as big on top in layman's terms. So it is BOT in short. So big on top, then there will be no horizontal asymptote. So I would call it no HA. HA for horizontal asymptote, okay? If the degree of the numerator is less than that of the bottom, so in other words, big on bottom, right? Big on bottom, then it's bo. Ooh, what is that? The second O here is actually saying that the horizontal asymptote is y equals 0 in all cases, okay? All cases of big on bottom. Then what if they're both equal? Then we would say exponents are the same. So then divide the coefficients, divide coefficients. So this is the third case. So in short, it's eats DC. Exponents are the same, divide the coefficients, okay? So we'll see all of these cases in our examples. So if you look at the second question, I'm choosing the second question just like that. There is no really reason why I chose this. 3x plus 3 over x plus 2, okay? So always I would start first by writing it in a factored form, which is already done in this case, or you can write it as, because 3 is a GCF, you may want to write it this way. It helps. And then I would find the asymptotes and the holes, which are the break in the journey in the rational functions. So if you look at here, there is nothing common for us to cancel. So there are no removable discontinuities. So there are no holes, none. Okay, so let's note that point. Next, we'll come to vertical asymptote. Whichever is left at the denominator, this whole thing, this is left out in the denominator. So equate it to 0 and solve for x, which means that the value of -2 substituted here will make the denominator 0, and that is what we do not want to happen. So that is where this particular asymptote lies, and its equation is x equal to -2, right? Now coming to horizontal asymptote, if you see here in all the three cases, this is an excellent case of each DC because both the exponents are same, the degrees are same. So if the exponents are the same, divide the coefficients. So you'll write it as y equals 3 over 1. The coefficients are the leading terms, right? So 3 over 1, which is y equals 3. So that is the next asymptote. So once we find this, it's easy for us to write the domain and range, okay? But before that, let's finish this x and y intercepts also. To find the x-intercepts, you would equate the numerator after cancelling, right? Equate numerator to 0, meaning you're finding the zeros from the numerator. So here, x plus 1, if you equate it to 0, you will have x equal to -1. So that's the intercept, x-intercept. So -1, 0 is the x-intercept. How do you find y-intercept? It's the same thing all through the any graph function, any functions, that if you substitute x equal to 0, plug in x as 0 in the original function, then the y value will become 3/2, isn't it? So that becomes the y-intercept. So this is 0, 1.5 or 3/2. Okay. So now let's write the domain and range. So the domain of this function would be all the values of x, all the real numbers, x belongs to all real numbers, such that x is not equal to -2. This is in the inequality notation, right? And when it comes to the range, then you would say y belongs to all real numbers such that y is not equal to 3. That's it. That becomes the domain and range. You could definitely write this in interval notation also. So you try it. I would love to see what you do. And now let's draw the graph quickly. So first we have to start with the vertical and horizontal asymptotes. So x equal to -2. So from here, this is a -2. So all the asymptotes are always drawn as dashed lines. Okay, so we should remember that. And y equals to 3. So as soon as we draw the asymptotes, we must name them, right? Okay, that's like good students behavior, right? We have to give all the details. And the position of the graph here or there will be decided by the x and y intercepts. So they say that the x-intercept is at -1, 0, which is right here. So for sure, the graph is going to be this and that way, okay? And the y-intercept is at 0, 3/2, which is somewhat here, okay? So now, you just eyeball it for now. You can actually see the same graph in Desmos. Maybe I should use a different color for the actual curve. So the curve will always be on the opposite side, right? So this is how the graph would look like. All right. I hope this helps. We'll do more examples in my second part. Thank you for watching. I'll see you next time.